Spectroscopy 2A. Nuclear magnetic resonance spectroscopy. Low resolution proton NMR. The essential idea is that analytical techniques can be used to determine the structure of a compound, analyze the composition of a substance, or determine the purity of a compound. Spectroscopic techniques are used in the structural identification of organic and inorganic compounds. Nature of science. Improvements in instrumentation. Mass spectroscopy, proton nuclear magnetic resonance, and infrared spectroscopy have made identification and structural determination of compounds routine. Models are developed to explain certain phenomena that may not be observable. For example, spectra are based on the bond vibration model. The basis of NMR spectroscopy. NMR stands for nuclear magnetic resonance, and the applications are, first, you can determine molecular structures using NMR, and also MRI, magnetic resonance imaging, is the same thing. They called it MRI instead of NMR because they thought nuclear would scare off medical patients. That's why it's called magnetic resonance imaging instead of NMR. The region of the electromagnetic spectrum used is radio waves. It's a very low energy radiation and it's non-invasive. You can listen to the radio. Obviously radio waves are passing through your house if you have the radio on. How does proton NMR spectroscopy work? In two very small bullet points, we'll simplify it. Well, hydrogen atoms in molecules interact with radio waves in a magnetic field. And depending on the chemical environment, the nuclei in the hydrogen atoms will absorb different amounts of energy. So what does it tell us about molecular structure? Well, it tells us the number of chemical environments for hydrogen atoms and the number of hydrogen atoms in each environment. We've got methane over here, and you can see we've got 1, 2, 3, 4 hydrogen atoms, but each one of them is in the same environment. Okay, so there's one chemical environment. A chemical environment for a hydrogen atom relates to where the hydrogen atom is in a molecule and the kinds of neighbours it has. Let's have a look at this one. We've got one hydrogen here bonded to the carbon, and we've got another hydrogen here in a hydroxyl group bonded to this oxygen. So there's two chemical environments, and there's one hydrogen in each chemical environment. This is for the fans of physics out there and just people who are generally curious. Some nuclei have a property called nuclear spin. Only nuclei with an odd number of protons have this property. And for example, hydrogen does, carbon 13 does, fluorine 19, and phosphorus 31. Nuclei act like tiny magnets and line up with or against an external magnetic field. And they have different energy depending whether they're lined up with or against. And you can see this on this energy graph here. When the field's applied, you've got some that are against the field with minus half spin, and some with positive half spin that are with the field. The ones here can be boosted up to here when they absorb radio waves. They flip over from being plus spin, plus half, to minus half. So chemical environments, let's have a bit of a look at these. Let's predict the number of chemical environments and the ratio of hydrogen atoms in each one of these compounds. We've got propanol, and the chemical environments, we've got 3 hydrogens on this N-methyl group, which will all be identical. We've got the 2 hydrogens here, which are identical. We've got 1 hydrogen at the end here. So we've got 3 different chemical environments. And the ratio is going to be 3 here, 2 here, 1 there, 3, 2, 1. Next we've got propanone. We've got this methyl group bonded directly to this carbon, and another methyl group bonded directly to the carbon. So we've got 6 protons that are identical. So there's 1 chemical environment. so ratio doesn't apply there. Butanoic acid, we've got this methyl group at the end, we've got CH2 here, another CH2 here, slightly closer to this carbon on the carboxylic acid group, and we've got this hydrogen bonded directly to the oxygen. So we've got 1, 2, 3, 4 different chemical environments, and in ratio would be 3, 2, 2, 1. Next, 3,3-dimethylbutanoic acid. What we've got a methyl group, another methyl group, and another methyl group, all bonded to this carbon. So we've got 3, 6, 9 hydrogens all bonded to this, all in the same environment. Then we've got CH2 here, and we've got the hydrogen bonded to this oxygen. So we've got 1, 2, 3 chemical environments, and a ratio of 9 to 1. And finally, methyl ethanoate. We've got 3 hydrogens over here, bonded to the carbonyl group, and we've got 3 over here, which is bonded to the other side of the ether group. And so we've got 2 different environments, and it's 3, 3. Here's an image of a low resolution or a simplified NMR spectrum for methyl propanoate. It tells us the number of signals, tells us the number of different chemical environments for hydrogen atoms. So we've got 1, 2, 3 different environments, 3 signals, 3 different environments. The relative area under each signal, shown in the parentheses here, is the ratio of hydrogen atoms in each environment. So this environment, there's 3 hydrogen atoms, in this one there's 2, and in this one there's 3. So let's have a look at methyl propanoate over here. You've got 3 signals for the 1, 2, 3 different environments. You've got a ratio of 3, 2, 3, 3, 2, 3. And the chemical shift here, where it lies, can tell us what type of proton. And you can look at table 27 to see what that's about. Let's look in a more detailed NMR spectrum for ethanol. You see here it's got an integration trace instead of little brackets with numbers. Okay, the integration trace is used instead to show the relative area underneath the signal. The height of the trace corresponds to the area under each signal. So what information are we told here? Well, the number of signals tells us the number of different chemical environments for hydrogen atoms, and we've got 1, 2, 3. 1, 2, 3. Integration trace height tells us the ratio of hydrogen atoms in each environment. You can see this is the smallest one, 1, and we've got 1 hydrogen here. And this is 1, this is roughly twice that height, so it'll be 2, and that'll be the CH2 hydrogens. And then you've got down here, it's roughly 3, it's roughly 3 times this height, and that's the methyl group where there's 3. So you've got a ratio of 1, 2, 3. And again, chemical shift tells us which types of protons it would be. So as you can see now, the larger the ppm, you can see this hydrogen bonded directly to the oxygen has a higher ppm than the CH2, which is, again, these hydrogens are nearer this hydroxyl group. And here, with the smaller ppm, these are further away from this hydroxyl group. But we'll get to that later. Table 27 in the data booklet gives proton chemical shift values for hydrogen NMR relative to TMS. And you can see the full data table in the data booklet. You've got here chemical shifts of 0.9 to 1 for hydrogens in methyl groups, 1.3 to 1.4 for CH2 and carbon chains, for chemical shift of 1.5 here with the carbon in an end carbon. You've got esters, carboxylic acids, at the carbon double bond oxygen side. So these ones here have a shift about 2 to 2.5. Here we've got the ketone, and again, this shift is slightly higher than the chemical shift for the carboxylic acid and the esters. You've got methyl groups, which are attached to phenyl groups, 2.5, 3.5. You've got hydrogens on attached to triple bond carbons, 1.8 all the way to 3.1 depending. And you've got CH2 groups next to halogens, between 3.5 and 4.4. I will say that some chemical shifts do not exactly match the values in the data booklet here. Okay. Have a go at predicting the chemical shift in parts per million for these indicated hydrogen atoms in each molecule. Press pause and have a go. Okay, let's have a look. Did you get the following? Give yourself a nice big pat on the back if you got them all right. Okay, interpreting low resolution hydrogen NMR, match the signals with the structure. Example 1. We've got a low resolution NMR spectrum for methyl propanoate here. You can see that there's 3 distinct peaks, and you can see on the structure for methyl propanoate 1, 2, 3 distinct areas, and there's 3 to 2 to 3. We've got this CH2 group is going to be the middle one, and you can tell that just because it's 2, and it's got a part per million shift between 2 and 2.5 according to the data booklet. You've got this methyl group here, which is going to be shifted the least. It's furthest away from these electronegative oxygens, and it's got a peak of around 0.9 to 1.0. And finally, you've got the methyl group attached directly to the oxygen with a shift of 3.7 and 4.8. Well, let's determine the structure of this compound. Proton NMR spectrum for compound with the molecular formula C2H4O. We don't know if it's aldehyde or ketone. We know it's 1 to 3 according to the integration up here. The area 3, so there must be 3 protons, and it's got a shift of 2.2 to 2.7, so we know that that's a methyl group attached to this carbonyl group. And the area of 1, so it's 1H, and it's shifted to 9.4 and 10.0 parts per million, so we know that that's the hydrogen directly attached to the carbon in the carbonyl group. Therefore, we know that it has to be an aldehyde because of this hydrogen here. It's ethanol. Example 3. A compound with the molecular formula C3H8O is shown to the right here. And we're going to throw 3 possible isomers. We're going to have propan 1-ol, propan 2-ol, or methoxy ether. And we're going to identify the unknown compound from the number of signals on the spectrum and the relative area under each signal. First of all, A has 1, 2, 3, 4 chemical environments for hydrogen. The hydroxy group, the CH2 on carbon 1, CH2 on carbon 2, and the methyl group. And it's a 3 hydrogen, 2 hydrogen, 2 hydrogen, 1 hydrogen ratio. Here we've got this methyl group, which is identical to this methyl group. So there's 6 hydrogens altogether in one environment. We've got this 1 hydrogen on this central carbon and the hydroxyl hydrogen on the central carbon. So 3 different environments with a 6-1-1 ratio. And finally, here we've got the methyl group. Here, the CH2 and another methyl group attached directly to the oxygen. And that's a 3-2-3 ratio. And we can see that immediately 3-2-2-1, 3-2-2-1 must be the correct one. So A matches the spectrum, and so we can confirm that it's propan 1-ol. The group responsible for the signal at point 9 Here is going to be the one furthest away from this oxygen, and we've got this methyl group over there, the terminal CH3 group. Example 4. A compound with the empirical formula C3H7 is shown below. We're going to identify the compound and explain our answers. In fact, you're going to do that. Give it a go. See if you get it right. Pause. Okay. Well, the total number of hydrogen atoms from areas under the signal is 14. Okay. And we know that the empirical formula is C3H7. And so, simple math tells us the molecular formula is C6H14. We've just doubled it, haven't we? We've got two signals, two chemical environments, and a chemical shift of 0.9, which is going to be from its CH3 groups. So we've got to have two lots of them, because we've got 6 hydrogens. And then we've got a chemical shift at 1.3, 1.4. We know it's going to be these CH2 carbon chain type hydrogens, and we need how many of them? We need 8, so there's going to be 4 lots of these, and so we know that it's going to be hexane with the CH3 at the end and the 4 lots of CH2 through the middle. Example 5. Our compound has the molecular formula C3H6O. Predict the number and ratio of the signals in the hydrogen NMR spectrum for the 2 structural isomers and sketch the expected spectrum. Okay, well, here are the 2 isomers. We've got an aldehyde and we have a ketone. Chemical environments in the aldehyde, there's 1, 2, 3, and ratio is going to be 3:1. Over here, and let's work out the other one. We've got one group. The methyl groups are the same, aren't they? So we're just going to have 1. 6 for the ratio. So here we're going to have a peak for the methyl group down the bottom here, at just about around about 1. Then we're going to have the peak for the CH2 between 2 and 3, and then we're going to have a big jump up and a smaller peak up here for the hydrogen here. Oops. For the ketone, we'll have a single large peak between 2 and 3 here. Next we shall be looking at high resolution NMR, but that's the end of this presentation. Goodbye.